same time? What if you have something moving in both the x and the y? This is where you need what we talked about in 1.3, if you read that. I decided to skip it because it's really not helpful yet. So, gravity versus speed. So, without any initial speed sideways, we know what would happen to something falling downwards. The distance it travels every second will get faster and faster, will get further and further, creating an accelerated motion like A. Acceleration. This happens because gravity is constantly pulling harder and harder, accelerating the object. But we also know that objects that move sideways have constant velocities, unless there's something accelerating it. And so we would get a predictable motion, like here, constant motion to the side. And so when you combine those two, you end up with this pattern, B, and the trajectory of a object, it kind of arcs. If you've ever thrown something, you've seen this before. If you did our introduction to projectile motion assignment, you've seen this as well. And so some combination of the x direction motion, which is constant, and the accelerated vertical motion is going to create what we call a parabola or a projectile motion. So, projectile motion. This is when you shoot something in the air. Its initial speed could be horizontal, which might be a ux, or maybe a vertical speed uy, or, as you're going to see today, you could have both at the same time. It's important to know which direction the speed is going, because when you're moving in the air, you're always going to have the influence of gravity pulling towards the ground, affecting the vertical velocity. So, if you throw a bunch of things like these people did in an experiment, any horizontal motion will cause your object to move to the side as it comes down. The more horizontal motion you give, potentially, so we have right here, their first trial where they shot something straight up and it came straight back down. It took them 2 seconds to do this. Then they did a little bit of horizontal motion and it went like this. And it took a little bit less time because it didn't go quite as high. Then they did another trial where they went at about 60 degrees. And it took less time, but again, it didn't go as high, but it did go real far. They shot it for the third trial at 45 degrees, and it went the furthest out of them all. It took 1.451 seconds, and they got not a lot of height, but they got a lot of distance. Their fifth trial, they shot it straight 30 degrees. Didn't go as far as before, it actually went to the same distance as 60. And it didn't take very long at all. And their last trial, they did 15 degrees, the kind of typical calculus ones. And it didn't go, it went just as far as their 75-degree angle, and it didn't take any time at all. Why is this? Because as things are moving to the side, gravity's pulling them down. So the longer you're in the air, obviously, the further distance you'll travel. But if you're going upwards, you'll lose all that when you come back down. If you're going sideways, you might hit the ground before you can actually run out of speed. And so, this is kind of what's going on. And so, the question you need to look at yourself is, so if I were throwing something sideways and I wanted to go it as far as possible, which of these would I want to do? Which angle will get the ball going the furthest? Well, the answer is 45 degrees. Because your horizontal speed can be used for the maximum amount of time, and you're going to get enough time to go pretty far. This is the ideal, but just like walking through water, the air is going to be constantly pulling back on your thing, so in reality, you're not going to go quite as far. Air resistance, or what we're going to constantly refer to as drag, is going to constantly be pushing back on your object, decelerating it in the horizontal direction. Air resistance always always pushes in the opposite direction of your motion. And so for the whole time of this guy moving, there would be a pull backwards until eventually it starts to drop straight down. Historically, this is why people thought objects themselves have energies, and they just kind of run out of energy as they move, like humans who are trying to run. But we know it's more of the air resistance pushing back on them, decelerating them. So, thank goodness for air resistance. Without air resistance, we couldn't do fun things like skydiving or predict or slow things down as they're falling towards us, and we'd have a lot of dangerous meteorites and other things coming at us. So consider someone skydiving. At the beginning of our jump, we have 0 initial speed. And so we will get accelerated downward by gravity, and eventually that speed will cause some sort of air resistance to happen. And so we're going to start getting our acceleration down. We'll have some sort of a velocity. So we could probably find it if we know for how long we've been falling. But eventually, the air resistance is going to become so large that it will balance out our forces. No, gravity can't pull us any harder through the air because there is going to be tons of air pushing back on us. And this is where you're going to stop accelerating and have what we call constant velocity or terminal velocity, because it's the final speed you can reach as you fall. Super useful because you want to obviously not come crashing into the ground. You could also add a parachute to increase your air resistance and slow you down once you reach terminal velocity and get safer as you come down. But back to the motions in the air. How could we predict these predictable motions? Well, we have our equations for it. Of these variables, S, U, and A, are vectors. And so the direction you're going is going to be super important. You need to know if it's a vertical or a horizontal, because we can consider a horizontal motion or a vertical motion using our equations, but we can't put both in the same equation. So we could do some sort of a velocity to the side and an acceleration going down, but we can't do them together in the same equation. So for example, something thrown off a cliff, there is no acceleration in the horizontal direction. So you can get rid of this. If there's no acceleration, A is 0. All of this becomes 0. And so your equation is really just the distance traveled sideways will be your initial velocity sideways and how long you can move through the air. And if there's no initial velocity in the vertical direction because you shoot sideways, you don't have to worry about uy because that'll be 0. And so your distance in the vertical direction is just going to be your acceleration from gravity. Remember, this is always going to be gravity, or g, which is 9.8 meters per second squared. And so you can use these two simplifications for something that is thrown horizontally. But it's better that you actually just mentally think about through, do I have acceleration, do I have velocity, every time you're doing something, and just get rid of them in the equations. So this brings me to vector math, or what we called 1.3. This might be a review depending on what math you've taken. We'll see what's going on when you get there. So vectors are just values that have a direction associated with them. So when we're talking about them, we usually represent them in mathematical terms. So let's say this is 15 meters per second to the side, and we have 6 meters per second going down. How would you add two vectors together to find a total speed? Well, first of all, you can't add them the same way you would add normal numbers. Is it 6 plus 15? Is it 21? No, because it's not that simple. When we're talking about something like this, what you need to do is you need to consider the directions they're going. So this influence is actually going to create some sort of a vector that goes this direction. Think about if you were pushed by someone while you were already going to the left. If you were driving and you had a crosswind, you're going to end up going to the side. And so you can always figure this out by kind of doing some sort of a parallelogram situation and figuring out where this is going to end. It's called adding tip to tail. So we actually would use this magnitude of 6 meters per second and add it to the tip of this one. We'll end up down here. And so this is going to be my what we would call resultant vector, or this is what happens when I add two vectors. And so if you've taken math before, you probably recognize I just made myself a nice little right triangle with a hypotenuse unknown and a short leg of 6 meters per second and a long leg of 15 meters per second. So my velocity is going to be used per Pythagorean's theorem. So my velocity for this guy is going to be 16.15 meters per second. Again, you'd have to worry about sig figs in a real problem, but for now, this is the true velocity you're going, and it's not a velocity yet until we figure out what angle we're actually going at. So, what is my angle? We need to figure out, well, what angle is this? We have our numbers, so this would be the opposite divided by, so my angle, I know my opposite side, and I know my adjacent side. So we're going to use tangent to figure this out. Actually, we're going to use inverse tangent of 6 meters per second over 15 meters per second. The units actually cancel out, which is perfect because tangent is a dimensionless thing. So in your calculator, do inverse tangent of 6 over 15. My angle will be 21.8 degrees. So this person is going 16.15 meters per second at an angle of 21.8 degrees. So your true final answer, total velocity, will be 16.15 meters per second at 21.8 degrees. With respect to negative 21, because that's a -6 direction if we're talking about with respect to the horizontal. So this is how you would add two vectors. What about if we have a vector, a direction, and we want to be able to use our equations? So we can't do this equation until we know our ux and our uy. So I can't do either of those equations until I have an x or a y, because my acceleration is straight down, because A is only in the y direction. So I need to know my vertical version of my y to figure out some information, and I need to know my horizontal. So again, we need to know our angle, and we need to know our value. So let's say that this u is 25 meters per second, and let's say our angle is 30. To deconstruct one, all you need to do is again make a right triangle. That was a horrible right triangle, but pretend with me. And so my ux is going to be equal to the adjacent side, and my uy will be my opposite side of my angle. And so, again, we have some trig relationships here that will help us out. We have a hypotenuse, and we have an angle. So if we do this sine of 30 degrees, that will give me my opposite value, which is uy, over my hypotenuse, which is 25 meters per second. So I can find my uy by just multiplying 25 meters per second to the other side. And so uy is going to be make sure you're in degree mode here. .5 meters per second will be my uy, and it'll be straight vertical. To do ux, well, that's the adjacent, and the relationship for an adjacent is going to be a cosine of 30, which will be my adjacent side, or my ux, over 25 meters per second. So again, multiply 25 to the other side. So 25 times cosine of 30. My ux is not so simple. It's going to be 21.65 meters per second. Again, deal with your significant figures if and when you need to. So if I had to have two sig figs right now, I would just do some rounding. Then I could actually use these in an equation, like figuring out how long it takes the ball to stop or how long it's in the air. And these are some of the things you're going to want to practice. So for example, a scuttle, is flying horizontally with a speed of 4.2 meters per second, with an altitude of 3.1 meters. It drops a fish it's carrying, flounder. What horizontal distance will the fish go in the time before it lands? Well, so first of all, we need to figure out, it has a horizontal distance, right? We know its vertical velocity, its horizontal velocity is 4.2 meters per second. We know the acceleration in the y is negative 9.8 meters per second squared. Now, this depends on what coordinate system you set up. I actually might do positive y going down, positive x to the right. That might keep this a positive number so that we don't have to deal with negatives. You get to decide. And so we can't put those in the same equation because they're not affecting one another. The acceleration is not affecting his sideways distance. But we also have a vertical distance of 3.1 meters. And so we could use that vertical distance and the acceleration in our acceleration equation. Since we know there was no initial velocity to the downwards, to figure out t. So we're going to go ahead and do t. So 3.1 meters equals 1/2 times 9.8 meters per second squared times t squared plus 0. Go away. And so we solve for t. So you're going to end up with, so this is 4.9 divided to the other side. You're going to end up with 0.63 seconds squared equals t squared. And so t is going to be 0.79, round for now, but don't actually round, leave it in your calculator. So I did all of that math just so I could actually go back to the horizontal equation as x will be 1/2. There's no acceleration in the x. Bye-bye. So we're going to do, how far do we go? It's 4.2 meters per second multiplied by how long he's in the air. My total distance to the side is going to be 3.34 meters. Again, check your units. I can't have the 4, so 3.3 is my sig figs. Meters. That is the true answer that we wanted. You just needed to find t in the meantime to help you solve. Another problem. A soccer ball is kicked with an initial velocity of 2.4 at an angle of 32 degrees with respect to the ground. How far away will it land and how long will it be in the air? So again, this time we need to actually break up our initial velocity into its components. So if we have this triangle of 2.4 meters per second at an angle of 32 degrees, we can break this up into a horizontal and a vertical just by doing our cosines and sines. So our horizontal is going to be the cosine because it's the adjacent multiplied by our hypotenuse, and our uy is going to be the sine of 32 degrees multiplied by our hypotenuse. Again, drawing it out is going to help you figure out which one's sine and which one's cosine the best. Those are u's. And so we know our initial stuff. Is going to be 2.035, again, round later. And 1.27, oh, sorry for all my bad numbers. And so we can use those and the fact that we know that the only other thing we have is an acceleration in the y of 9.8 meters per second squared. Now this time I will keep that negative because my velocity was initially going up. So we're going to have a negative on the acceleration since the acceleration is pulling down. And so we can use that to figure out how long it's in the air. And then we'll use that time to figure out how far away the ball will travel. So if we know that we have an initial velocity, this one's actually slightly more complicated because we're going to go up until we get to 0 and then we're going to come back down. And so the cool thing about this is that acceleration is clearly acting the whole time and you're going to get a symmetrical thing. So when you solve this equation for velocity, and you go for the velocity equals 0, that's going to be half of your trip, and you can just double it because it'll come back down in the same amount of time. And so we can just double this. And so we know negative 9.8 meters per second squared is equal to our negative initial velocity. So negative, I had to for a second look at my numbers, 1.27 meters per second over t. We go ahead and we solve for t. It's going to take you a little bit of algebra. But your time for half of the trip is 0.129. So if you double that, time for the total trip is going to be 0.26 seconds. And so you can use that time to figure out how far it goes to the side. So we're going to go distance in the x. Again, there is no acceleration in the x, so a of x is 0. So all I need to do is the initial velocity multiplied by t, or 2.035 meters per second multiplied by 0.26 seconds. The more you practice this, again, don't delete things from your calculator, the better you're going to be at this. So my final distance in the horizontal is going to be 0.5, let's round up, 3 meters. So those would be the two answers to your problem. Total time in the air was double the time it takes to stop the ball in the vertical and make it come back down. 0.26, and then 0.53 is the distance it'll travel to the side in those times. All right. Hopefully that helped. You could have figured out how high it goes to by using half of the equation. I skipped a little bit of that in this problem, and I skipped and just told you that it's symmetrical. Hopefully you believe me, otherwise I can show you a problem where we do how high it goes up and how far it comes back down, and the fact that since acceleration is constant, the time will just be the same for the up and the down part. But if you trust me, it is just the same, so you can double the time. So that is motion in 2 dimensions. Hopefully this helped you understand. Let me know if you have further questions, and I hope that you do okay with this.